First of all, I would like to thank the organizers for providing me with the opportunity to give this talk. I will talk about additive and multiplicative functions, but somehow in a different way that we usually do. Usually, well, I assume you know what an additive function is and what a multiplicative function is. Usually we study, say, additive functions, and we look at, we examine their global behavior, say the average value that they have, and then also perhaps their local behavior, analyze how the consecutive values of a given additive function are distributed. And we do then we do the same thing with multiplicative functions. But we rarely compare both these types of functions. And this is what we will do today. First of all, some notation so that we all know what we're talking about. I'll let p plus n be the largest prime factor function. P minus n, the smallest prime factor. The psi of xy function, which counts the number of y friable numbers up to x. The phi function, which count the number of integers up to x which don't have small prime factors. The standard omega n function, which counts the number of distant prime factors. And I'll denote by A the set of additive function with f of 1 equal 0. M, the set of multiplicative functions, G. So f will always be an additive function, and G will always be a multiplicative function, with G1 equals 1, because some people assume G1 equals 0, but I ask for G1 equal 1. Then we'll define A star and M star, just the subset of additive functions which are strongly additive. That is, whatever exponent you put on the prime, it's always the same value. And similarly for the multiplicative functions. Okay, so what will interest us today is discounting function. Say you are given additive function and a multiplicative function. You want to count how many n's up to x such that f of n is equal to g of n. Okay, I think it is a very clear definition. So we will be interested, of course, to find those functions f and g for which e is somewhat large. Okay, some very elementary result to start with. First of all, we will always work with additive functions which are not always 0. So when I write an additive function, assume that it has at least, it's not 0 for at least one integer bigger than 1. Okay. And this is enough to guarantee that if you look at another multiplicative function, then this additive function will differ from any given multiplicative function infinitely often. That is, this condition guarantees that f of n is different from g of n infinitely often. It's an easy exercise. Now, okay, to a trivial observation, if you are given an additive function, then it's easy to find a multiplicative function such that e of x is bigger than x over log x. It's trivial, because if you are given all the fp's, just take gp equal to fp, and that's it. Your e of x will at least be as large as x over log x, because it coincides on the primes, and then if you add the prime powers, it's even bigger. And so, but we're not happy with just this trivial observation. Let's keep going. Given any c, I should have written here any c positive smaller than 1, strictly smaller than 1, you could always find an additive function and a multiplicative function such that E of x is such that they coincide on a set of positive density. And it's easy to do. Just take a subset of the primes, which is very thin. So I denote the set of all primes by P here. Take a subset such that some of the reciprocals of the elements in that subset converges, and then define a multiplicative additive function f simply by taking f of p equals 1 if p is in S, and 0 otherwise. So most of the time it's 0, in other words. Then it's an easy exercise to show that f of n is 0 on a set of density, positive density, just the product of 1 minus 1 over p, which converges obviously because sum of 1 over p converges. And then just take and define g strongly multiplicative by just fixing gp equals f of p for all the primes outside of S. And then it's easy to see that they coincide at least on some set R and then we get on the same set R, sorry, and then we get E of fgx be equal to cx. Now, of course, you can take C as close to 1 as you want because you can take the set S to be very thin, say with only one prime, a huge prime, and then this product will be close to 1. So you can get very close to 1. Okay, now let's consider right away the example of f of n equals small omega of n. And you will see I will state some theorems that would hold for a much larger family of additive functions, but in order to keep, because I'm going to go through some proofs, just to keep the proof simple, it's much better to go with a particular case omega, the omega function. Okay, so we take f equal to omega. Okay. First observation, well, we already knew that E of x for this omega of n function is bigger than x over log x, but we can find a larger set of coincidence in this way. And this is, it's easy because just choose g of p equals k to 1 over k. So k is fixed. Take gp to be of constant value on all the primes and to be k to the 1 over k. And then it's easy to see that for those n for which omega of n is equal to k, then g of n is just k 1 over k with exponent omega of n, which is equal to k and which is omega of n. So g of n is equal to omega of n very often. On those elements n for which omega of n is equal to k. And we all know that the counting function for those omega of n equals a k for k fixed is asymptotic to x over log x times this expression. And it's certainly bigger than some c from some point on. That's also not too hard to prove. So we're done. We've proved the star. Okay. So we did some little progress. We got x over log x times something fairly small. Not as big as we would like. So I will state now 4 theorems. And we will go through the proofs. It's not so complicated. The first theorem is that if you fix epsilon bigger than 0, then you can find a multiplicative function which coincides with omega on a large set. And the counting function for that set is at least x over log x. Remember, we had just x over log x before. Now we have x over log x, 1 plus epsilon. I can get rid of the epsilon later on, you will see. But I will have to put a slowly increasing function beside the log x, nevertheless. Okay, and okay, so we will see this later. The second theorem tells us that we can find a much better lower bound, a much bigger lower bound, but it doesn't work for all x. It works on a particular subsequence of real numbers which tends to infinity. The third theorem I will not state now because you're not psychologically ready for this. It's just that it needs a lot of notation and stuff, so I don't. We'll come to it later. But it will tell us that we should not be too ambitious in our approach. And then finally, Theorem 4, which I find is the most interesting, is that you cannot be too ambitious. I mean, given with omega, you cannot find a multiplicative function such that these two functions, omega and g of n, coincide on a set of positive density. It would always be small O of x. Okay, let's go with Theorem 1. You'll see, I will give a sketch of the proof. And, okay, so I fixed delta to start with. And you can imagine that later on I will take it as an expression of epsilon. And I construct a sequence of prime numbers. I start with S1 equals 2. And then for each j bigger or equal to 2, I define Sj as the smallest prime, but that's larger than the previous one, but also larger than j to the 1 plus delta. And this is to ensure that the set of primes so chosen has the property that the sum of the reciprocals smaller than plus infinity. So that's why I take the g to the 1 plus delta. That guarantees that. Okay, and then I define g, the multiplicative function, that candidate that will satisfy the inequality of Theorem 1, to be a strongly multiplicative function, which is 1 most of the time, but which is the index of that prime number if the p in question is equal to one of those primes in S. So I define it as j. Okay, this is just an observation which I will need later on, is that the proportion of positive integers divisible by a fixed element of Sm is just 1 over Sm minus 1 times a constant which depends on that sequence of primes, S1 up to S1, S2, and so forth. And it's easy to see that we obtain that. And the important is the C delta at the end, which is this the value of this infinite product, which converges, of course. Okay, now let's take X large, and we define L1 and L2 as log log x minus log log x to the 2/3 and log log x plus log log x to the 2/3. And I will be working with the interval L1, L2. And most of you see why I do that, because most of the integers up to x have a number of distinct prime factors which belongs to the interval L1, L2. I could even have taken log log x to the 1/2 plus some epsilon, say, instead of 2/3, but I allow myself this luxury because I don't need more. Okay, then clearly this is E omega g x, this quantity. It's obviously bigger than if I sum over all these sets, the number of elements in all these sets, just when j varies in this interval L1, L2. I lose a lot, but so what? It will be enough for my my needs. Certainly, for each fixed j, the number of elements in that set up there is bigger than if I pick some elements n small equal to x, which are divisible by Sj, the jth prime in that big set, that small set of primes in a sense, but which has no other divisors belonging to S. So it's got, when you look at the factorization event, it's just got one of those candidates. It's got to be that jth one and no others. And then if I write that otherwise, the third line here, bigger or equal to this set, it's really bigger or equal. It's not equal necessarily because it's implicit there that I demand that Sj squared does not divide n. I just want Sj to divide n. And then obviously omega of m is j minus 1. Okay, now for x large enough, recall that Sj is bigger than j to the 1 plus delta. But if it can be, remember those j's are in L1, L2, they're big because it depends on x and x is big. So I can assume that Sj is smaller than j to the 1 plus 2 delta. I could even be instead of plus 2 delta, I could take plus 3 half of delta, whatever. But I just want to stress that this is possible. And then j, of course, is in the interval, so it's smaller than that. And then if x is large enough, then it's smaller than log x to the 1 plus 3 delta. No problem. Okay, so this is interesting because I do that because I want to get rid of this Sj at the bottom there on the fourth line on the screen. I want to get rid of that because I don't want to depend on j. I want an expression that depends on x. And since Sj is smaller than log x to the 1 plus 3 delta, then I can do that. Okay. But I'm stuck with this here. I don't like this here. This is embarrassing, and this also. So what do? Okay, so I just repeated the same line so that you could see where I'm going. Now, if we sum over all the j's in L1, L2, because this is okay for all the j's in L2, I get that this is bigger than that. And then, of course, then omega, the range of omega n is in an interval. And then, okay, but I don't like this condition here. I would like to get rid of that. Well, if we get rid of that, we don't get, it's no problem, because it doesn't happen often. That is, the number of m up to that quantity, where omega of n is outside that interval, is very small. It's small of that. It's well known. So then I can introduce this error term here. And then since I want to get rid of that condition, well, I just have to sieve with all the primes in Sk, and this is when I obtain this C delta, which is the product of 1 minus 1 over Sk, where k goes from 1 to infinity. And then we're done, because I only need to take delta equals epsilon over 3, and there I am, 1 plus epsilon. And this, I want it to be bigger. So this is a constant, so it's not important. So that's essentially the idea of the proof, fairly simple. I will state Theorem 1 in a more general context in the end. Okay, Theorem 2 says, okay, we can improve the lower bound, but it will only work on a subset of the real numbers. Okay, the sketch of the proof, I start out exactly the same way. There's my set. Again, the sum of the reciprocal of the primes in there converge. But then I introduce another sequence, and it's obviously a sequence that increases extremely fast. E to the 2 to the g. You will see why I picked that particular sequence in a moment. And okay, now fix a j, fix an integer j, and look at that set under there. All those integers small equal to rj over sj, such that sk does not divide m for each sk in S. Then for a fixed j, this set, forget about the omega n equals j minus 1 for now. For this set, the number of the m's have a various number of values for omega of m. Well, pick zj to be the one where which has the largest number of largest value for omega of m. So this is very well defined. Because I will state the theorem in a moment of Balazar. You know that if we look at the counting function for those integers n up to x, such that omega of n is equal to k, this function is unimodular in k. It increases, then it reaches the maximum where k is about log-log-x, and then it decreases. So there is a maximum value out there. And I write it as zj minus 1. Okay, now we define g differently than before. Recall before we defined g of p to be j, the index of that prime in the set S. Now I define it as zj. It's different. And then it's one outside of S. In other words, one most of the time again. Okay, now I consider a different interval, but also remember I had a fixed interval, L1, L2. Now it's not fixed, it varies with J. So it's now I need the full power if possible, so I take the optimal value 1/2 plus epsilon in the exponent. Okay. So, and then again, we know that the number of integers smaller than or rj over sj for which omega of n is outside of that interval is small of this. Now, some of you might say we don't have log rj over sj everywhere here. We just have rj. But it doesn't matter. The thing is, rj increases so fast that it practically is the same, essentially the same interval if we have rj or rj over sj. Rj is e to the 2 to the 2 to the j, while sj is a reasonable value. So, okay, so we are allowed to state this here. So, here I go. There's the small o of rj over sj at the end. So, the number of elements up there is the sum of for all the news in ij. And plus a small o of this error term that I introduced. Now, by the very nature of zj, look at this set. Remember that it reaches the maximum value when omega of m is equal to zj minus 1. So this is smaller or equal to the maximum value. And how many elements are there in the interval? Well, it's 2 log rj to the 1/2 plus epsilon. So this inequality is clear. Now I will reverse this. I will use this quantity here, bigger than that sum divided by 2 log j. And here it is. So this is exactly the operation that I did just now. Okay, now, on the other hand, this quantity at the numerator, forget about the error term. This quantity at the numerator there is, again, like we did before, is 1 plus smaller 1 c to the delta, c delta rj over sj. So what I get in the end is, okay, so I get that this is bigger or equal to 1/2 c delta rj over sj log rj. Now I want to get rid of the sj. So I have to find an upper bound for the sj. I'll do that in a second. Just to recapitulate, what I got is this. E to the omega j rj is trivially bigger or equal to this. And then is bigger or equal to that quantity. And then if we sum over m, as we did before, so this is the last line we proved in the preceding slide, this very last one here. Okay, now, like I said, I want to get rid of the sj at the bottom here. Again, I do about the same thing I did before. Sj is, well, it's bigger than j to the 1 plus 2 delta, but it's smaller than j to the 1 plus 2 delta. And then for delta and epsilon fixed, then I can write this. It's bigger than 2 to the j. And remember, recall how I chose rj. Rj was e to the 2 to the j, so we have equality there. 2 to the j epsilon is log. So the important thing to remember is that sj is smaller than log rj to the epsilon. So I can replace, so this was the last line of the preceding slide, and replace sj by this, and I get my result, and we are done. We did improve the lower bound, it's much bigger. but it only works on this particular sequence of integers. Okay, of real numbers. Theorem 3. Okay, this is the one I tried to hide from you. This says that, remember, when we picked, constructed our set of primes, we defined it GP to be 1 almost all the time, except that on a particular set of primes S, we picked it at one time to be J, at one time to be ZJ. What about something else, you know, different from 1? That would help us better, perhaps to improve that lower bound of Theorem 1. Well, tough luck. Can't work that easy, because we're on a certain set of real numbers, it will spoil. I mean, it will be smaller than x over log x to the 1 minus epsilon. So we can't hope to take that 1 plus epsilon down, say, to 3/4. We can't do that, because we can't get it below 1 minus epsilon, at least. With this method, with this particular method, of course. So I'll sketch a proof really quickly. I define 2 sets. Those integers which have all their primes P in Sj. Sj is the set of primes for which f of p is different from 1. And then B to be the set of integers for which all the prime factors are outside of Sj. In other words, f of p is equal to 1. Okay. The union of these 2 sets is not the set of natural numbers, but there are particular sets which will become very useful in a second. Okay, since we have that the sum of the reciprocal of the primes converges, then the sum is reciprocal of a's in that a there converges. This is essentially the infinite product, 1 plus 1 over p plus 1 over p squared and so forth. So it converges. And then if I define Cj, if I restrict the sum of the reciprocal on certain values of g, then I will get a constant time proportion of the Cj. So I certainly have the sum of the Cj smaller or equal to 1. Okay, now we fix some epsilon, and we construct a sequence yk, which is essentially k squared. Okay. Why take k squared plus 6 epsilon? The reason is, in the next line, is that if k is large enough with such a definition, the intervals will be disjoint. Okay, they will come and there might be a gap in between them. I don't care, but they will be disjoint. I think with 2 plus 5 epsilon it works. It works as well, but plus 6 it definitely works. Okay, now take the sum of the Cj's for j in this interval gk. Since the sum of the Cj's, all Cj's is small or equal to 1, we certainly have that it's for k large enough, it's smaller or equal to this. Now, it means that for infinitely many k's, we have dk smaller or equal to 1 over k. Otherwise, the harmonic series would converge. So, for not all k's, but for infinitely many we have. So we will restrict ourselves from now on these particular k's for which dk is small or equal to 1 over k. And then I get the following. Okay, the setting xk equals e to the yk, because I want yk to be log xk in a sense. And then for these particular k, we have that of course, E omega j xk is this definition, it's that, for the sum of the j in those interval gk, plus those outside. Now, those outside are not very numerous. And for this, I use a result of Tenenbaum in his book on analytic number theory, the 2008 edition. He has a result, a consequence of which is this one. We all know that this quantity here is small O of x. We know that. As soon as psi of x goes to infinity. But we have a measure of that. And it's this one. It's very strong. e is smaller than x e to the minus psi of x. So, squared. So if I take psi of x equals to, psi of xk equals to log x xk to the epsilon, this accounts for the error term I have over there. Okay, so now what do? Is I take this e of omega jx for these j in gk, and I write each n as a times b, because any integer can be separated in those which are the prime factors that are in a, and the others which are in b. Okay, so then I count it this way. I fix a, I sum, and then I count all the b's small equal to xk over a. And then I obviously get this expression. Now I use a result of Balazar, which I already mentioned, which says that pi k of x is unimodular in k. And this was a conjecture of Erdős, by the way. And he proved that in the 90s. And it's attained when k is log x plus big O of 1. Then it's easy matter to compute that pk0 of x will be x over square root log x. And actually, I don't need that strong result. I just need that it's big O than x over square root of log x. And then if you use that, you get that the expression up there is smaller or equal to some constant c, xk over a, then the square root of log xk over a, but that you can get rid of, you can forget about the a, it's not too hard. And then you get this. So obviously you're going to take this expression out of the sum, and you're stuck with the sum of 1 over a, which is easy to estimate because the sum of 1 over a is simply, remember it's those a's that for g of a equals j. And then we get for that Cj, so we sum over all this j in gk, and this is equal to dk. That was the definition of dk. And remember that we chose only those k's for which dk was small or equal to 1 over k. So that allows for the next line. I carry this awful error term there, which is of no concern. Now we want to replace the k there. This k at the denominator, we want to get rid of it. So what was it? Remember, yk was k to the 2 plus 6 epsilon. So I have k equal to that, and then it's bigger or equal to yk to the 1/2 minus 2 epsilon. It's not too hard to prove. And then yk, remember I took xk to be e to the yk, so yk is log xk. And then I just replaced that, and here it is. I obtained this, and this ends the proof because I just wanted this to be smaller than a constant time xk over log xk to the 1 minus epsilon, but it's minus 2 will do. Minus 2 epsilon will do. Okay, this ends the proof of theorem 3. And let's move to theorem 4, which says that whatever multiplicative function g you pick, it will never be equal to omega on the set of positive density. And this is the sketch of the proof. First of all, of course, we only need to consider those n's such that omega of n minus log x is smaller than log x to the 3/5. Now I'm very generous. I could take 1/2 plus epsilon, but I'll just take 3/5. And then I define a particular subset of the natural numbers, fix d and k, and we introduce this set t, which is those n which for which the largest prime factor is bounded by d, so they're d-friable. And also, I don't want big exponents in there. Okay? So if k equals 1, I don't want any squares. I just want square-free numbers. If k equals 2, I don't want cubes, and so forth. The interesting thing about this set is that it's finite. it's finite, because if I didn't have this last condition, it would be infinite. But since I add this last condition, it is finite, so it's more maneuverable. So I just repeated it. And then I consider those integers, the set of integers with no small prime factors, and this is the counting function with this phi of xd, which I already defined. Now, what about this? Those integers which have a large exponent in their factorization? The counting function for that is small also. sk of x, it's easy to show that it's smaller than x to the 2 to the k. So you see that if I take k large, it will become very small. Okay, now I write a lemma, which is very important, interesting. Take a multiplicative function, so g is fixed. Consider each integers in 2x, which are for which the number of prime factors is close to log x, so close to log x to the 2/3. Then write each of these integers, their factorization in the product of two integers. Say the un part, the bad part, that is those that allow a large prime factor or allow a large exponent, those are my bad part un. And then the nice part, tn, well, where the a is not too big and the primes don't exceed d, the prime factors. Now, the statement is the following. If you have two integers n1 and n2 smaller than x in this close to omega of n and so forth, to log x and so forth, if on these two integers n1 and 2 the g and the omega function agree, and if they have the same bad part, u1, u2, then there's something very particular about the good part, the nice part. They have the same number of prime factors. Okay, it's not obvious right there. I will go through the proof very quickly. You'll get the idea. The fact that the omega n is close to log x is crucial. Okay, oh yeah, in other words, I like to write this because it's more easy to understand. If they have the same un part, then their tn parts have the same number of prime factors. Okay, what I do is, this where I use the fact that the set T is finite. Since it's finite, and assuming that g of n is different than 1 for at least one integers, if it's always 1, it's disqualified right away. I mean, it's not going to be close to omega of n, no worry. So that means that if I look at this expression vdk, the minimum of all possible values where g of n, with the quotient g of n with g of m, then it's bigger than 1. D and k is fixed, T is a finite set, this V has to be bigger than 1. So I take x large enough so that vk is bigger than 1 over log x to the 1/3. And I first show, that will almost end the proof, I show that g of t1 is equal to g of t2. If I can succeed to do that, since this is trivial, if these two quantities are equal, then means these two quantities are equal. But remember what n1 and 2 is. n1 is u1 t1, and then this is u2 e2, and then u1 is equal to u2. This is what I assumed. So then omega of t1 is equal to omega of t2, and this is what I want to prove. Okay, so I assume they're different. If they're different, then the maximum value of these two possible quotients is bigger than v. That's the definition of v. It's bigger than that. So say omega of n2 is bigger than omega of n1. It could be the other way around, but say it's arbitrary. So I take this one. Then we have trivially omega 2 is omega of n1, omega n2 over omega 1. And this is bigger because omega of n is close to log x, remember? And then this quotient up there, because of the second line up there, is bigger than 1 over log x. So we have that this is bigger than log x and so forth. And then the other way around, omega n is too small. I do essentially the same kind of reasoning, and I get that it's too small. So the distance, so if I repeat the slide there, then the difference between omega of n2 and omega of n1 is too large. It's outside my interval. So it contradicts the fact that it was inside the interval. So it means that G1 is equal to the GT1 is equal to GT2, and then I get the result. Okay, where do I use that? Okay, I get that E omega Gx is this sum. What I do is I take all the integers n smaller than x, for which g of n is equal to omega of n. I write n as the bad part times the good part, u times t, and then plus an error term which comes from, because I want to get rid of those large exponents, introduce an error of x over 2k. Then the small O of x is to account for those n outside my interval log x minus log x 3/5 and so forth. Then I sum over u, and this allows me to write, look at those upstairs there. They have the same bad part u. And then they all have a certain number of prime factors, but they all have the same omega of t. So I just need to take, this is an upper bound, I take the worst case scenarios, the maximum over the possible values of z, that is of omega of n, and then I get that. So then I separate this, I will go quickly because I have 2 or 3 minutes left. I separate that in a various sum, y, and then I'll show you the sum, don't be afraid. It's always the same thing on the right, but I study different ranges, all the ranges. And the reason I do that is if you take any one of these, this is very complicated to evaluate because there's 2 conditions there. But depending on the range, I get rid of one of these conditions or the other one or both of them. And then it's much easier to evaluate. So for instance, if you take the third one, which is defined up there, then it's easy to see that it's actually equal to this expression where I got rid of the t and tdk because it's obvious that it's satisfied. Then I used again this result of Balazar, and I get an upper bound, this is just technical, and I get x over square root of log 3d. Now, I do about the same kind of reasoning for each of these sums, and in the end, actually the worst case scenario is sigma 3. So then the sum of all these sums is no bigger than that. So if I take, in the end I get this. So if I take d large enough, I will get that this is smaller than, say, epsilon x, and this also smaller than epsilon if epsilon is fixed at the beginning. And there you go, you get the result. Now, we've got 1 minute left. The general statement is the following. If you construct a set of primes, so it's such some of the reciprocals converges, and if you have this additional condition here, in our case, lambda x was log x plus log x to the epsilon, 1/2 plus epsilon, then we get this result. And this gives a better lower bound for omega of this E omega G, which is in the simplest case where you take k equals 1, you get x over log x times triple log x to the 1 plus eta, which is better. And you could also get log x, triple log x, and then fourth log x to the 1 plus eta, and it would be also work. This is what I just said there. This is the proof of the corollary. Okay. Final remarks in 30 seconds. Most likely this bound can be improved. Okay. Somehow, if we could take d as a function of x, maybe it could be improved. I could not do that. Most likely, the result holds, even if we don't have equality, but close. Say, if g of n is close to omega of n, and somehow the whole thing will work anyway. So it means that not only omega of n is not equal to g of n on a set of positive density, but it's impossible for a multiplicative function to be close to omega of n on a set of positive density. And even perhaps we have the fact that this particular set here is of density 0. That is, you can't even get as close as log x to 1 minus epsilon. Perhaps log x, but not log x to 1 minus epsilon. That's it. Thank you very much.
Thank you for your nice talk. So is there any question? Yes.
What if you move the argument?
Say that again?
What if you move the argument? Instead of saying g of n is close to omega n, you say there is a small shift of n. So g of n plus this shift is omega n.
G of n plus a, say.
Yeah,
but
for some small a.
Yeah, but then it's a shifted. Then we don't have multiplicativity. Yeah, it's an interesting question. I don't have the answer.
Any other question? Okay, so let's thanks again.